Anyway, our next speaker is Chris Cashen, who will talk about RAAGedy right-angled Coxeter groups.
RAAGedy right-angled Coxeter groups, yeah, thanks. Okay, so the question here is, if we give you a right-angled Coxeter group, can you tell me, is it quasi-isometric to some right-angled arc group? Yes or no? And if yes, if I give you the right-angled Coxeter group in terms of a presentation graph, I'd like to know what's the presentation graph for the RAG, or a RAG that it's quasi-isometric to. So just definitions for these acronyms. What are these groups? Both of them you define by a finite simple graph, and this gives you a presentation. Presentation is you take one generator for each vertex of the graph. Each edge of the graph tells you that those two vertices commute, so you get a commutator relation in your presentation. And for the RAG, that's the whole thing. And for the Coxeter group, you add some additional relations that says the square of each generator is trivial. And okay, both families of groups, these are non-positively curved, right? They act on cube complexes. That's basically the Cayley-2 complex for the presentation. So what that means is the vertex set is in bijection with the group elements. Two vertices differ by an edge if those group elements differ by multiplication by a generator. And if you look at a cycle where you read off one of the relators, you should fill in a 2-cell along that cycle. And the tilde is just that in the Coxeter group case, if you do exactly what I said, since the generators are order 2, you'd get these bigons. Right, so the same generator going in both directions and filled in by a bigon. And we want it to be a cube complex. We don't want the bigons there. So in the Coxeter group case, just smash those bigons and think of it as a single undirected edge. So on the RAG side, the edges will be directed where the generators have infinite order. And in the Coxeter group case, it'll be undirected edges. And so these cube complexes have names, right? For the right-angled Artin groups, it's acting on the universal cover of the Salvetti complex. And the presentation graph is telling you about the positive part of vertex links. And on the Coxeter group side, it's acting on the Davis complex. And the presentation graph is really telling you the full link of a vertex. So here's first examples. So my presentation graph here has vertices red and blue, so two generators for my group, one edge, so one commutator, so they commute, so this is a z squared, and the universal cover of the Salvetti complex is just the square tiling of the Euclidean plane. And the group action is by translation, so the red generator translates in the direction of the red arrows and the blue generator in the blue arrows. And on the Coxeter group side, so here's an example presentation graph for a Coxeter group. So I have 4 vertices, so 4 generators. Each of them has order 2. For the red and the yellow, right, there's no edge. So here there's no relation that involves red and yellow, and there's no relation that involves blue and cyan. But blue and cyan both commute with both of red and yellow. So this group's a direct product of 2 infinite dihedral groups. And the Davis complex is, again, the square tiling of the Euclidean plane. And the link of a vertex here is the full circle, which is this graph. And on the right-angled Artin group side, you just look at the outgoing edges, and the link connecting them is this graph that we started with. Okay, so our question is, right-angled Coxeter group, when it is quasi-isometric to a RAG? And before we talk about that, why would you care about such a question? I mean, one reason you might care is it's just a fundamental question. These are 2 families of groups that we like. They're not positively curved. They're used for lots of interesting examples. If you claim to be doing geometric group theory, you should try to understand, are these groups the same or are they different? Furthermore, there's a huge body of recent work on the QI classification for RAGs. And so if you wanted to know something about the QI classification for right-angled Coxeter groups, maybe the first question you ought to ask is, am I already QI to some RAG? And then declare this to be somebody else's problem, right? Declare this to be on the RAG side. Or more practically, there's all this machinery for RAGs. When does it apply to a right-angled Coxeter group? Am I close enough to a RAG that I can still use the same kind of techniques, or is there some kind of geometry that's totally different that's going to mean none of this works? Okay, so let me start narrowing the problem a little bit. So add two qualifiers here. The group should be one-ended and two-dimensional. One-ended is not a serious restriction, so there's a standard reduction in this field due to Papasoglu and White that says whenever you're doing quasi-isometry type of questions, you should first reduce to the one-ended factors of the group, and you study those. And that completely answers the question for the bigger group. So we know how to reassemble one-ended pieces back to the original group. The two-dimensional restriction, this is a serious restriction. So one thing that it does for you is it makes the presentation graph simpler and makes certain statements easier to deal with, but there's a geometric reason that we need this that I'll mention later on in the talk when it comes up. And two-dimensional here really means that the cube complexes are two-dimensional. So 2 dimensions is the highest dimension of cells. In terms of the graph, two-dimensional in both cases means that the presentation graph is triangle-free. And for the one-endedness, on the RAG side, that means your presentation graph is connected, and on the Coxeter group side, that means your presentation graph has no separating click. Further restriction, is there a fly on the screen now?
Yeah.
Yeah, okay. So add a quadratic divergence condition. So divergence is a QI invariant that tells you how fast geodesics in your space sort of separate from each other. And we know for RAGs that that should be at most quadratic, right? That's a theorem of Baerstock and Charney. And so Coxeter groups, they have a wider spectrum of divergence that can happen. So if you hope to be QI to a RAG, you must restrict to quadratic divergence. And this has been completely described when that happens. So there's this property, CFS for the presentation graph. So I won't tell you what that means, but the point is, if you want to know quadratic divergence, there's a condition that you write down for the presentation graph and you check it. So we only need to worry about CFS graphs. Okay, so here's an old result that we're going to try to generalize in a few minutes. So if you tried to run this in the other direction, when is a RAG quasi-isometric to a Coxeter group, or this is an even stronger condition, when is it commensurable to a right-angle Coxeter group? The answer is always. So Coxeter groups are like a proper superset up to coarse equivalence of the RAGs. Okay, so I want to tell you how that works because we're going to try to generalize it. So how do you go from a RAG to a right-angle Coxeter group to which it's commensurable? So you start with delta. Delta is the presentation graph for the RAG, and you construct a graph double, which means you take the vertex set of delta, you double it, so you get 2 vertices for each of them, and then whenever there was an edge in delta, there's 4 possible edges upstairs that cover that edge, and you add all 4 of them. And then the theorem is when you do this operation on graphs, you get commensurability at the group level. So A delta is commensurable to the Coxeter group that you get from the double of delta. And actually, the Salvetti complex and the Davis complex are isomorphic cube complexes in this case. And this was our original example, right? So I take the red vertex, I double it, that becomes the red and yellow. The blue one doubles to the blue and cyan. And the single edge here becomes the 4 possible edges, and the 2 cube complexes were isomorphic complexes. So these two groups, I mean, you know, we can tell in this example, right? The RAG is Z squared, and this I said was the product of 2 infinite dihedral groups, so that's a virtual Z squared. And we want to do all of this in terms of the presentation graph, so in the other direction I should tell you, if you have this graph gamma defining your Coxeter group, can you recognize that it's a graph double? So can you recognize that this is the kind of thing that would have been commensurable to a right-angled Artin group? And yes, you can. This is easy, in fact. So terminology here, 2 vertices in my graph are twins if they have the same link. So they have the same set of neighboring vertices. And a twin module means a maximal collection of twins. And then, so this is module in the graph theory sense. This is a standard construction that you can take module decompositions of a graph and you can get like a quotient graph from them. So here we can get a twin graph. The graph breaks up into the union of its twin modules, and for each of those you put a vertex and then you connect them by an edge if the join of those twin modules was contained in your original graph. And then the easy fact to check is that your graph gamma is a double if and only if every twin module has even order. And here's an example of this. So here's a graph. Right? Here are its two twin modules. They both have size 4, so this graph is going to be a double. And the way you can prove that is you just look in each twin module, you pair up vertices however you like, and then you make a graph out of that. So this pair here becomes a vertex, each pair becomes one of the vertices, and if the join of those was in the original graph, then you put an edge in the new graph. So this graph on the left, this is the double of this graph on the right. It doesn't matter which choices you make, right? For any pair of twin vertices in the graph, there's an isomorphism of the graph that exchanges those and fixes all the other vertices. So choices are irrelevant. Okay, so what I want to do in this talk, I want to tell you 3 things. One is this, as I said, a generalization of Davis and Januszkiewicz's construction, or the sort of the reverse of the construction. So how do I make my right-angle Coxeter group quasi-isometric to some RAG? And there the strategy is going to be to try to modify the presentation graph until it's a graph double, and then apply the inverse of Davis and Januszkiewicz's theorem. And then in the other direction, I'm going to give you two ways to rule out being quasi-isometric to a RAG. So obstructions that mean that you're not raggedy. One is building ladders in the maximal product region graph, and one is finding compliance cycles. Okay, so the first part. So what we want to do is find operations that change the presentation graph for the Coxeter group, but don't change the quasi-isometry type of the group. And in the paper, there are 3 of these. I don't know if you can tell. This one is supposed to be faded out. So I won't talk about unfolding. I'll talk about link doubling and cloning. So link doubling, this one is old. This is well known. So you have your presentation graph, and you pick some vertex in there. You can define a homomorphism to the cyclic group of order 2 by killing all of the other generators except for V. So then you get a short exact sequence, and it turns out that the kernel here is another right-angle Coxeter group, and you can describe its presentation graph explicitly in terms of the one that you started with. What you need to do is you delete the vertex that you were interested in, then you double what's left, but for vertices that were in the link, you then identify the 2 copies. So in pictures, here's a graph. I'm going to double over the link of this vertex 5. So 5 doesn't appear on the right-hand side. Its link is these 2 blue vertices, 3 and 4, and so for those I only get 1 copy of each of them on the other side. And then the 3 black vertices, I get 2 copies of them. A copy here and a copy sort of reflected on the other side. So the right-angle Coxeter group defined by the graph on the right is an index 2 subgroup of the right-angle Coxeter group defined by the graph on the left. And now observe that sometimes you can turn a graph that's not a graph double into a graph double by applying this operation. So this graph is not a double. There are 3 pairs of twins, but this vertex here and this vertex here have no twin. So those are singleton twin modules, right? Size 1 is not even. So this isn't a double. But the link doubling lets me sort of delete vertices at the price of multiplying the rest of the graph by 2. So let me try to eliminate this vertex. So I'm going to double that. Its link is in blue. That's going to stay fixed. And then the black vertices are going to double. And so one of the vertices went away, and the other problem vertex is still there. But now I can try again. Right? Double over the link of that vertex, and I get a doubled octagon. So by passing to an index 4 subgroup, I put myself into a situation that I can apply Davis and RAAG's theorem. Okay, the other operation is called cloning. I'm going to pick a vertex in my graph, and then I'm going to make a new graph where I add, so I pick a vertex v, I add a new vertex v prime, and I attach it to all the vertices in the link of v. So in the new graph, v and v prime are twins. So here's my graph. I pick the vertex v, its link is in blue. I add a new vertex v prime, and I attach it all to the link of v. So you can't just clone any vertex you like. There's a condition. So v is a satellite of w if the link of v is contained in the link of w. And what we need is, if I want to clone v, so if it's clonable if it's a satellite of at least 2 other vertices. And then the theorem is, if your vertex is clonable, then when you do this cloning, you don't change the quasi-isometry type of the Coxeter group. So I'm going to skip the proof of that theorem, just for time, so don't look. Okay, and so what's the application? So here's how we extend Davis and RAAG. So you have a 1 and a 2-dimensional right-angled Coxeter group. It is quasi-isometric to a RAAG if you're in one of these 3 conditions. These are increasingly more general. So first, let's look at the first one. So this tells you sort of where the cloning comes in. So what are the twin modules? If all of the twin modules of gamma are even, you're already done. That graph is a double, and so it's already commensurable to a RAAG. So there must be some odd twin modules if we need to keep working. If you have an odd twin module that is not a singleton, so it has at least 3 vertices, well, a vertex is a satellite of its twins, right? Its twins have exactly the same length, and satellite is, I just need a containment of links. So if you're in a twin module of size 3 or higher, those vertices are clonable. So go ahead and clone it and turn that odd module into an even module. So the places that you're still worried about are the singleton modules that only have 1 vertex. That vertex may or may not have been clonable, depending on what the rest of the graph looks like. If it is clonable, go ahead and clone it. That turns the twin module into size 2, and we're happy. So the only problems that we have after cloning are potentially the unclonable singletons. And then the next 2 conditions tell you sometimes you can get rid of those using the other operation, using the link doubling operation. And so the proof is going to be that if you're in this case, you can do a link double once to bump you up to this case. So you can eliminate one source of problems. And then if you're in the second case, you can link double once to get into the first case where you know how to solve all of the problems. So the conditions are contained in each other, but the proof is to work upwards. So let me give you an example. So here's a graph. Here are the twin modules. So there's 2 twin modules of size 2. Those ones we're happy with. Right, there's 1 of size 3, but those are clonable then, so I can clone one of those vertices, and I won't have to worry about that. That's an unclonable singleton. That's an unclonable singleton. That's a singleton that happens to be clonable, but for the purposes of the example, what's more important is to notice that this yellow vertex is a satellite of this red vertex. So the first step is going to be get rid of that twin module of size 3. So go ahead and clone one of those vertices and make it size 4. And then I'm going to start attacking the unclonable singletons with link doubling. So let's first link double over this guy. It goes like that. And the important fact here in the statement of the theorem, right, we needed these problem ones to be adjacent. And the reason that we needed the problem ones to be adjacent is so that when I link double this one doesn't proliferate, right? It's still a single red vertex here. This yellow one did multiply, right? I've got the yellow one here and there's 2 copies of it down here. But what happens is both of those are still satellites of this red one. And so in the next step, when I link double here, the yellow ones again multiply, but they multiply into twins of themselves. right? So this pair of yellow ones are twins, and this pair of yellow ones are twins. So in this graph now, every twin module is even. So this graph is a graph double. And it's a graph double of this graph here. So conclusion was the right-angled Artin group defined by the graph in the upper left is quasi-symmetric to the right-angled Artin group in the lower left. And the horizontal step across the top, that we only know as a quasi-isometry. We don't know that it's commensurability. This vertical side, this is passage to an index 4 subgroup, and this is Davis and Januszkiewicz commensurability. So the composition we only know as a quasi-isometry because of that cloning step. Okay, so that was the sort of positive direction. If you're hoping that you're quasi-isometric to a RAG, here's a way that you can try to prove it. Try to modify your graph so that it becomes a graph double. And so now we're going to talk about two ways to try to obstruct being quasi-isometric to a RAG. So the first one is ladders in the maximal product region graph. The starting point for this is the theorem of Sang-Rock-Oh, who is here. So if you have questions about this, talk to him during the break sometime. So what's the statement? So there's a bunch of terminology that I'm not going to define, but I'll tell you on the next slide what it means in terms of right-angled Artin groups and right-angled Coxeter groups. Okay, so the theorem is you have a quasi-isometry x to y, where x and y are universal covers of compact weakly special square complexes. And the conclusion is that such a quasi-isometry must take maximal standard product regions to within uniformly bounded Hausdorff distance of maximal standard product regions. This is where the dimension 2 restriction comes from. This is really a theorem for square complexes, so two-dimensional cube complexes. So to be able to apply this, we need this kind of restriction. The idea here is you want to try to control the flats in the space. And the reason the two-dimensional is important is because then maximal flats and top-dimensional flats are the same thing. If you had a higher dimensional complex, you might face a situation where you had a maximal 2 flat. So maximal, it's not contained in a 3 flat, but it's not top-dimensional. And in those kind of cases, I mean, there's other work in the literature where you can get around such problems, but you often have to work hard and put extra conditions on your group. So like in RAGs, there's work like this, but you have to make additional assumptions like that the outer automorphism group is finite to be able to say that you can control these flats that are maximal but not top-dimensional. And I think Sang-Rock has a counterexample in 3 dimensions. No? Oh, okay. Okay, so there is hope that this theorem can be extended, possibly by adding additional hypotheses, and we'd like to know more about that, but at the moment this is what we've got. So corollary of the theorem is you can make a graph that encodes these maximal product regions. So that's this pi. So you take a vertex for each maximal standard product region in your cube complex, and then you put an edge between them when 2 of these product regions intersect in a standard product region. And what you get from the theorem then is that your quasi-isometry induces an isomorphism of this graph. Okay, so I didn't tell you what compact weakly special square complexes means, but I assert that the universal cover of the Salvetti complex and the Davis complex in the two-dimensional case both are of this type. So the ones that we're interested in, this theorem applies to them. What does standard subcomplex mean? It means if you have your defining graph upsilon, you choose any induced subgraph you want, upsilon prime. That has its own cube complex, which sits as a subcomplex of the first one, of the bigger one. That's a standard subcomplex. And any translate of that is a standard subcomplex. So that's what the standard subcomplexes mean. They're the ones that you get by choosing subgraphs of the presentation graph that you started with. And then the same thing for the Davis complex. Maximal standard product regions, maximal standard product subcomplexes, they're the standard subcomplexes that are maximal products. So for it to be a product, what you want is that the subgraph you're choosing was a join. And for it to be maximal, what you want is that that join was a maximal join in your presentation graph. And for the Coxeter case, it's almost the same, except there's this extra word thick in here. So I want thick joins. The only difference is in the Coxeter group, you could have a join that's a subgraph joined with a single vertex. And then upstairs, that's not a satisfying product. I want my product regions really to be products of two infinite subcomplexes. So by thick join, I just mean that the two factors of the join both give me infinite subgroups or infinite subcomplexes, not just going off a single vertex. Okay, and then we want to observe that from that, you can say actually that you can immediately see the fundamental domain. So you've got this graph, right? And by definition, it was invariant under the group action. So the group acts and it's got a compact fundamental domain, which you can read off just from the presentation graph. You just look at the maximal joins in the presentation graph and make those vertices of the fundamental domain. And if they intersect in a join, then that's an edge in the fundamental domain. Why is it called RIC? Well, when Sang-Rock did this, he added also higher dimensional cells, and he called this object the intersection complex. And I didn't like that name, but I did like the name RIC for the reduced intersection complex, so we kept that. And I hoped one day I would give this talk in front of Rick Wade. So what you're supposed to think of for this object is some kind of curve complex analog for weakly special square complexes. For RAGs, there was already work doing this. Kim and Coberta had something called the extension graph, and then Wang had a similar kind of construction. So these are very closely related to this object, and I think the motivation for Sang-Rock was to sort of generalize that construction to more general square complexes, more general special square complexes. But yeah, if you're really interested in RAGs, there are already objects that are very close to this one. For Coxeter groups, there was a different attempt to make cube complex analogs through hierarchically hyperbolic structures on these groups. And so Abbott, Baerstock, and Durham in particular had a way to construct stability recognizing spaces for them. So what that means, again, this is something that the curve complex does for you for mapping class groups. So there's a notion of stable subgroup, which is a subgroup that is both itself hyperbolic and is convex with respect to, or quasi-convex with respect to quasi-geodesics. So it's Morse and hyperbolic. So that's stability. A stability recognizing space is a hyperbolic graph that your group acts on such that a subgroup is stable if and only if the orbit map gives you a QI embedding into this graph. And so, okay, I didn't tell you what CFS means, so I won't tell you what strongly CFS means. But for nice enough Coxeter groups, this maximal product region graph that we have is equivariantly quasi-symmetric to the space that Abbott, Baerstock, and Durham made. So then you might say, why don't we just use their space instead of a new space? This space is better. For this purpose, this space is better because quasi-isometries induce isomorphisms of the maximal product region graph. But for Abbott and Baerstock and Durham's space, quasi-isometries only induce quasi-isometries of their space. So in a sense, this product region graph is sort of more rigid with respect to quasi-isometries. But we are going to use their result. What we get from knowing that you're quasi-symmetric to a stability recognizing space is that you are also a stability recognizing space. So in particular, if I take two vertices and their distance in the graph is more than 2, or even more generally, if they are not the diagonal of some square, then the infinite dihedral group that they generate should QI embed into this maximal product region graph. Okay, so this theorem is basically in Sang-Rock's paper, just not stated quite like this. So the maximal product region graph for a RAG is a quasi-tree, but it's a quasi-tree in a particularly nice way. So what does that mean? So if you were a tree and you take a geodesic segment, then every vertex in the interior of that segment separates the two endpoints. Right? In a tree, there's no way to get around vertices that lie on a geodesic between 2 points. So that's a zero bottleneck condition for trees. In this setting, what happens is I take my geodesic, and if it's sufficiently long and I pick a point, gamma t, sufficiently away from the endpoints, I don't want to claim that that particular vertex separates the endpoints, but something nearby almost separates the endpoints. So any point in the interior of my geodesic, there's some v nearby so that the star of v separates the endpoints. So it's a one bottleneck condition. I have balls of radius 1 that separate points as long as those 2 points are far enough apart. And the sufficiently large and close are both something like the diameter of the fundamental domain. So what you should think of is that the fundamental domain for the action, this might be some complicated, highly connected graph, but the product region graph itself is basically built from these pieces in a tree-like fashion where neighboring pieces overlap in stars of vertices. So in the Kim-Koberda version of this, this is actually true, and in Sang-Rock's version, it's basically true, as the theorem describes. So the important takeaway here is far apart points, you should be able to find a star of a vertex that separates them. The catch, right, is that you don't know what your target RAG is, so you don't know what far enough apart means. So the idea is you should find an unbounded subgraph that can't be separated by stars, and then for any RAG that you specify, you'll be able to find far enough apart points that they're too far to be contained in a single copy of the fundamental domain for that RAG, and so it can't match up with any RAG. Okay, so here's an example construction. So here's a graph. I'm going to build up its fundamental domain for the action on the maximal product region graph by enumerating the maximal joins in here. And so this vertex is colored because you'll see that it's contained in every maximal join. And this edge is colored because you'll see that it's not contained in any of the maximal joins. Okay, so there's one maximal join. It's a K23. There's another one that overlaps it in a square, so these are adjacent in the fundamental domain. There's another one that overlaps the previous one in a square, and then the graph is symmetric, so then there's going to be 2 more. And so like I said, this vertex was in all 5 of those, so this, as a generator of the Coxeter group, this generator, it's going to fix the entire fundamental domain. And this generator, that was only in the first join, so it's going to fix that vertex but not the other 4. This one is going to fix only the red one but not the other 4. And because they're connected by an edge, those 2 commute, they give you a little order 4 group. So the 2 of those acting is going to give you 4 copies of the fundamental domain that make a square. This will be easier to see in a finite index subgroup, so I'm not trying to trick you, I'm just redrawing the graph. It'll be convenient for the next slide, so convince yourself real quick that those are the same graph. And then here, let's see, this was the graph we started with. I'm going to pass to an index 4 subgroup by link doubling over 4 and 5. So the rest of the graph here in purple, so that survives. That's exactly a copy of it. And then there are 4 more, or 3 more, so 4 total that make a square. And all of those maximal joins are still in there. So you're going to get 5 joins in a row here, and then 5 in a row here, and 5 in a row here, and 5 in a row here. So for this writing a Coxeter group defined by this graph, the fundamental domain for its action on the maximal product region graph is this square of side length 4, where this red vertex here, so this was the one that was contained in all 5 joins, it's going to fix one side of the square. And another copy of it here, the blue one, it's going to fix the opposite side of the square. So the square itself can't be separated by a star of a vertex, but that's not enough, right? I could have a RAG who's, so in fact, what are there, 20 vertices here? So if you take a 20 cycle, this will be the fundamental domain for the action of the RAG on its product region graph. So just having one graph isn't enough. I could just make my fundamental domain for the RAG bigger. I need to now extend this to be an infinite graph. And so that's where I'm going to use the group action and the fact that we had the stability recognizing space. So take Q to be this square, and then we had these two generators, R and B, that fixed exactly one side of the square, and then just start working on it with that group action. So that infinite dihedral group tiles out a ladder. So this is the word ladder, is this graph. So infinite in two directions, and in fact this group is QI embedded, so this is a two-ended subgraph, but it's too highly connected to be separated by stars of vertices. So this graph can't fit inside the maximal product region graph of any right-angled Artin group. You should worry a little bit that I haven't shown you like the whole product region graph. Maybe there are other edges, maybe this thing is not as nicely embedded, but yeah, trust me. In this example, it works out the way that I'm claiming that it does. What you see is really what you get. So you get this subgraph that can't be separated by stars of vertices, but it's two-ended, so it doesn't fit into any RAG. And something I like about this theorem is the product region graph, maximal product region graph for this Coxeter group, it might still be a quasi-tree. I think that it is. We don't know how to prove that, but I think it is still a quasi-tree. Right? It's just not a quasi-tree with exactly a one bottleneck condition. You need a bigger bottleneck condition. So here we really need that the quasi-isometries are inducing isomorphisms of this complex and not just quasi-isometries of it. We really get a fine invariant from knowing this extra information. Okay, so the last construction. This is going to be something completely different. So another obstruction to being QI to a RAG, but this one is really particular to Coxeter groups and RAGs rather than like understanding this product region graph and comparing. So let me remind you some facts about projection in cat0 cube complexes. So in a cat0 cube complex with the combinatorial metric, suppose that you have some convex subcomplexes. There's a well-defined closest point projection map to such a subcomplex, and in fact it's Lipschitz, so it's distance non-increasing. And if I take two convex subcomplexes and project them to each other, the results on both sides are convex subcomplexes and they're parallel to each other. So there's like a bridge lemma in this case that says there's a subcomplex that's a product, that realizes parallelism for these two subcomplexes. Okay, I want to not say things separately for right-angled Artin and Coxeter groups here, so let's just say that upsilon's my defining graph, my presentation graph. G of upsilon is either the right-angled Artin group or the right-angled Coxeter group, and sigma of upsilon is the square complex. So standard subcomplexes I defined for you before, these are always convex. These are convex subcomplexes. And so here's an extra fact that's true in right-angled Coxeter groups and right-angled Artin groups. If I have a pair of parallel edges in my square complex, they're labeled by the same generator, and there's an element of the group that commutes with that generator and takes one edge to the other. And here's a picture. So I have my parallel edges E and E prime. Parallel, so there's a string of squares connecting them. And the point is that all of my squares are labeled by commutators. So opposite sides of the square always have the same label. So if the label down here is S, then all of the horizontal edges are labeled S. And S commutes with A1, and S commutes with A2, and S commutes with A3, so it commutes with their product. So the product will be the G in this claim. Okay, so what's going to make this work is that for RAGs, there's a dichotomy in projections of standard subcomplexes. So if you have two standard subcomplexes in the universal cover of the Salvetti complex of your RAG, and you project one of them to the other, there's only two possibilities. It can be a single vertex or it can be unbounded. It can't be a finite complex if it's not a single vertex. Here's a picture. So Y and Z are my two subcomplexes, right? And then I project Z to Y and Y to Z, and I get two subcomplexes. And now if those are not single vertices, then there's some parallel edge in there. And from what we said on the previous slide, this edge parallel to this edge means they're labeled by the same generator, and there's some element G that commutes with that S and takes one edge to the other. But now your standard subcomplexes of a RAG, right? That S is an infinite order element of the RAG. So if there's an S edge here, there's also another S edge coming out of it. And there's an S edge coming out of it over here as well, right? But G still commutes with those edges. So you can just keep going and build a whole grid. So on both sides, there's a bi-infinite geodesic where every edge is labeled S, and the same element G gives you that those two bi-infinite geodesics are parallel. So as soon as your projections of standard subcomplexes contain a single edge, they actually contain bi-infinite geodesics. Okay, so good. So we'll use those facts in a minute. So the compliant subsets and subcomplexes, the motivation here is we know from Sang-Rock's theorem that maximal standard product subcomplexes are well behaved under quasi-isometry, meaning they go uniformly Hausdorff close to other maximal standard product regions. And the compliant subcomplexes, we want to sort of extend the class of subcomplexes for which this is true. We want other subcomplexes that are well behaved under quasi-isometry. So what we're going to do is take all the maximal standard product subcomplexes and allow you to project them to each other and take the subcomplexes that you get by doing that. So take the smallest family of subcomplexes that contains all of the maximal standard product subcomplexes and is closed under projection. So that's a compliant subcomplex. A compliant subset of my presentation graph is a subset such that the corresponding subcomplex is compliant. And then the theorem is if you specify in advance L and A and N, there exists a D, so that if my two presentation graphs have at most N vertices and there's an LA quasi-isometry between them, then all of the compliant subcomplexes go to within bounded D Hausdorff distance of compliant subcomplexes. Okay, so the D doesn't depend on the particular subcomplex, it's determined for you in terms of L and A and N. So now here is where we're going to get an obstruction to being a RAG. Suppose in your Coxeter group, in the presentation graph for your Coxeter group, that you have this kind of configuration. So what this is saying, the S's, these are compliant subsets of the presentation graph, and the P's are just paths connecting them in the presentation graph. And you want 5 conditions. So the first 3 bulleted conditions, they're just telling you that this picture is accurate. Okay, so the first one, the various paths P sub I are disjoint from each other, and their union is an induced subgraph. So there's no extra edges of the graph that are connecting vertices of different of the PIs or vertices like within a given PI, except for the ones that are shown. The second condition is saying how do the paths intersect the compliant subsets? Only at 2 vertices, only at the first and last vertex leading up to that compliant subcomplex. The third one is N is allowed to be 1. So you could only have the 1 as 0, but if you do that, you really insist that the P0 sort of leaves and come back. It can't just be a single vertex contained in S0, right? That wouldn't be interesting. The 2 starred conditions, these are going to have geometric consequences in a minute. So you should think of this condition as saying that the S0 is disjoint from the SIs. It doesn't actually have to be disjoint, but you want the intersection to be small. So you want it to be a clique so that the subcomplex where they overlap is bounded. And then this is a condition that says S0 is sufficiently independent from P. You want S0 basically not to commute with any of the P's. So you want for each vertex in the, okay, so not this vertex that touches S0 or this vertex that touches S0, but for every other vertex in any one of the paths, you want its link to have a small intersection with S0. Now, I would like to claim that if you have such a configuration, you can't be quasi-symmetric any RAG. I don't know how to prove that. So this theorem doesn't have as nice a statement as I would like. So the way that it's going to go is we're going to, Suppose this happens, and suppose that you are quasi-symmetric to a RAG, and then derive a bunch of restrictive conditions, and then in practice you would look at your gamma and hope that you could refute one of those conditions. But the geometry of it, we'll see in the proof here, what kind of things happen. So suppose you have this kind of configuration. The motivation for this description, so if you had a closed cycle graph, right, and you took the Davis complex of that right angle Coxeter group, that would be the universal cover of a closed surface. Right? So this is just a fact about Coxeter groups that are easy, that we know. This P, the union of the paths, it's not a closed cycle. Right? It's missing some edges. It's missing these edges where it could have gone through each of the compliance subsets. So the Davis complex of this subgraph P, the union of the paths, it's not the universal cover of a closed surface, it's the universal cover of a closed surface in which you've punctured some of the faces. You've punctured the faces that corresponded to these edges that don't actually exist. So it's a surface with boundaries, so its universal cover is like a thickened tree. Right? It's uniformly thick, or at least there's a bound on how thick it is because there was some finite surface that you were building from, but it's got these boundary components. So it's some kind of a fat tree. And each of the boundary components is contained in a single one of a translate of a single one of the SJs. Right? Because that was a missing edge that was contained in exactly one of the SJs. Okay, one of these is the S0, so let's take that to be the one along the bottom. So this boundary component at the bottom is contained in a standard subcomplex X0 here, which is the Davis complex of S0. So I want to focus on that one, and then I want to take a tubular neighborhood of it in this Davis complex of P. So I take some long subsegment of this geodesic, say length R, where R is large compared to whatever other constants we have. And then I also go out distance R in the tree direction everywhere from that segment. Okay, and then I cut off that finite part of this fat tree. Each of the boundary components that's left, that's in one of these translates of one of the other SJs. And now that it's finite, I can just number them cyclically as I go. Okay, so there's an X1, an X2, and an X3. Each of those belong is some translate of some SJ. And what I've accomplished here, it's like this Davis complex of P is like the scaffolding, and I've attached the standard subcomplexes that I actually care about, and I know now that X1 comes close to X2 far out here away from X0, and X2 comes close to X3 far out away from X0. X3 came real close to X0, but it also comes close to X4 far away from X0. And the star conditions that I didn't really explain, but I said they'd have consequences, here's the consequence. All of these Xi's, any one of them, if you project it to X0, you get something bounded. So that's what those conditions are telling you. So I have this cycle of compliant subcomplexes so that when I project them down to X0, each individual projection is small, but I told you at the start I wanted this geodesic to be long. Right, so I have a lot of small projections that are adding up to a large distance. And now if you suppose that you had a quasi-isometry to some RAG, now we want to contradict the projection dichotomy for RAGs. Right, so what happens, so the fact that these were all compliant subcomplexes means my quasi-isometry takes X1 close to some compliant subcomplex Y1, and the same for each of them. So Xi is uniformly Hausdorff close to some Yi. And the geometry of it works nicely, right? If X1 was close to X2, far away from X0, then Y1 is close to Y2, somewhere far away from Y0. So I can choose uniformly short little paths here, connecting Y1 to Y2 and Y2 to Y3, but stay far away from Y0. And then if you like, you could connect these all, right? So in each Yi, just choose some path in that subcomplex connecting the two short red ones. So those might be real long, but the red ones are the ones that we care about. But now this whole path going around, right, that's a path where both endpoints are in y0. Projection to a standard subcomplex is Lipschitz. So the projection of a path is a path. So if I project this path down, I'm going to get a path in y0 that connects these two distant vertices. But the blue paths project to single vertices. Right? This was the projection dichotomy. So the fact that each xi had bounded projection to x0 is going to imply that each yi has bounded projection to y0, but if it's bounded, it has to be a single vertex. So every blue path projects to a single vertex. But they have to add up to something big, so the red paths must be, at least one of the red paths must be projecting to a non-trivial edge in y0. So some epsilon I has non-trivial projection, which means it has an edge here that's parallel to an edge of y0. So there's a whole chain of squares connecting them, where all of the horizontal edges are labeled by the same generator, and then the vertical edge commutes with that. But now take that, so if that's G, this group element that commutes with all of the horizontal edges, take all of y0 and translate it by G, and call that y prime. So you get to translate this y prime that contains one of the edges of epsilon I, and it contains a geodesic that's parallel to a geodesic of y0. And now you want to pull this back to the Coxeter group side. So apply the inverse quasi-isometry. So this is where we ended up on the previous slide. There's a y prime that's a translate of y0, and it contains an edge that's parallel to an edge of that one. And so if you pull this back by the inverse quasi-isometry, you get some compliant subcomplex x prime. It should have coarsely equivalent, so x prime and x0 contain coarsely equivalent quasi-geodesics, the preimage of the parallel geodesics. They're in the same QI orbit because we conjugated group multiplication by a quasi-isometry. And this quasi-geodesic here comes close to a point that's far away from x0. So that gamma prime is a very non-convex quasi-geodesic. And so now we want to say that somehow we can rule this out. So you look at different, there's different things you could try to rule out. You can try to rule out any of these three conditions, and there are different examples where we do that kind of stuff. But a nice one is if S0 of our compliant set, S0 is square free, that means x0 and x prime are hyperbolic. And if they're hyperbolic, they can't have these badly non-convex quasi-geodesics. So this is impossible if S0 was hyperbolic. Okay, so here's an example. So here's a graph. The S0 is going to be this segment of length 2. That's square free. It's compliant because this is a maximal join, 26017. So that's like this half of the diagram. That's a K23, that's a maximal thick join. And 28013, that's like this part of the diagram. That's another maximal thick join. And S0 is their intersection. And intersection is a special case of projection. So this is one of our compliant sets. And there's a path P that's connecting two vertices in there. And it has the property that if I look at the interior vertices of that path and take the link of this vertex, it intersects the red thing in only one vertex. And so this satisfies the theorem, but the S0 is square free, so this can't be QI to any red. So the conclusion, how well are we doing? Well, we enumerated the 3,938 isomorphism types of triangle-free CFS graphs with at most 11 vertices. This is what we found. So this is the ones that are QI to some RAG, and this is the ones that are not. The planar and non-planar distinction, there was an earlier paper of Nguyen and Tran who handled the planar, the case where the presentation graph was planar. So the planar part of the diagram was already known. So what are all the abbreviations? DJ is Davis-Januszkiewicz. So these 11 graphs are the ones that were already graph doubles. CND is coarse near double. So these ones are the ones that, using the link doubling and cloning, you can reduce your graph to a graph double and see that it's QI to a RAG that way. And the operation of unfolding that I didn't talk about, there's 42 more graphs that if you allow unfolding and cloning and link doubling, that you can see that those ones are QI to a RAG. DL I didn't talk about. This is, Danny and Lefkowitz have a different approach to proving that certain Coxeter groups are QI to RAGs. On the non-RAGedy side, CC is compliant cycles, right? So this sort of region here, these are the ones that can't be QI to any RAG because of the compliant cycle. And L here is ladders. So these ones are the ones with ladders in their maximal product region graph. And so you do all of this, check all of these by computer and see what's left. It turns out that there are 8 graphs left with 11 vertices to which none of our techniques apply. And so these ones we don't know yet whether or not these are QI of some RAG. And those 8 graphs are these. The end.
Other questions?
Can you go back to the previous slide?
Yep.
So how does, like, how is it distributed? I cannot quite keep track of the counting. Like, is it evenly distributed between RAGedy and not RAGedy, or?
I mean, it's sort of close, but I think that's an artifact of having small graphs. I would guess that as the graphs get bigger, a larger and larger proportion should be non-RAGedy.
So you think that, you know, for very big graphs, most of them are not?
Yes. That'd be my guess, yeah. Yeah.
Remember Davis and Yanskevich proposed 2 graphs, 2
Yes.
Coxeter groups conventional writing direction groups. So
Right.
you tried using the other graphs as well?
The other graph is not triangle free. Yeah, so Davis and Januszkiewicz's proof actually is not directly to do the commensurability that I told you. There's a second right angle Coxeter group involved that's higher dimensional, and both of these sit as finite index subgroups in the bigger one. But yeah, we chose not to look at that one because it's got lots of triangles. It's a really high dimensional thing. Yeah.
Can you explain quality, like where quasi-isometry
Why it's a quasi-isometry and not a commensurability is just the construction is purely geometric and there's no algebra involved. I mean, I don't know that they can't be commensurable. I just know that the construction that we do is geometric, yeah.
So you don't know whether it's...
We don't know.
Okay. Thanks.
And I don't know how to tell. I mean, if they are quasi-isometric, I don't know how to tell that they're not commensurable in that case, yeah.
Are there commensurabilities between RAGs and right-angle Coxeter groups that don't come from Davis-Januszkiewicz construction?
Yeah, Danny Lefkowitz's construction are, it's finite index RAG subgroups of right-angle Coxeter groups. Yeah, so even the question of when a given right-angled Coxeter group is commensurable to some right-angled R group, this is a long open question as well. And we don't really have any good ideas how to approach that, except that if you prove that they're not even quasi-symmetric, this proves for you that they're not commensurable. But yeah, the other direction, we don't touch that at all.
So did this allow you to say something about quasi-asymmetric classification of right-angled Coxeter groups?
That'd be nice. I mean, we hope to be headed in that direction, but this was the first step, yeah.
What is known in higher dimensions?
Not much. Yeah, we'd also like to understand that better.
But is the assumption that like the complex actually two-dimensional versus like virtual multiple dimension 2 actually feels very essential, or do you think that would...
So let me say this. I strongly suspect that Sangrok's theorem, and therefore most of what we've done, should go through if you don't have three-dimensional Euclidean subspaces, which actually is not triangle free for the RAGs. The right condition there is that the defining graph doesn't have a cosahedron. So there should be a sort of easy-ish generalization that says you can allow three-dimensional cells as long as you don't have three-dimensional Euclidean subspaces. But in the real higher dimensional thing, yeah, you need some way to get a hold of the flats. I mean, what you want is to be able to say that all of the top dimensional flats are close to standard flats. If you had a way to say that, then you could start making progress.
Okay, if there are no more questions, I'll thank Chris again.